All right, let's just jump right into this explainer. Today, we're going to decode a concept that totally transforms chemistry. Taking it from this static, boring textbook idea into a vibrant, ongoing tug of war. We're exploring the wild world of chemical equilibrium. This is where reactions aren't just a simple, straightforward start-to-finish thing. Instead, they're this continuous, highly dynamic dance that, honestly, never really stops.
So we usually think of chemical reactions as having a super clear start and end, right? You mix A and B, they fizz, maybe they pop or change color, and eventually, bam, you get C and D. It feels like a total one-way trip. But what happens when they actually leave behind a pretty massive amount of unreacted material? Like, what happens when a reaction just flat out refuses to cross that traditional finish line?
To figure this out, we're going to build our knowledge step by step through 5 crucial stages: the dynamic balancing act, measuring the stalemate, the degree of dissociation, Le Chatelier's principle, and finally, the thermodynamics of equilibria.
Section 1, the dynamic balancing act. Let's start right at the foundation by looking at the 2 fundamental types of chemical reactions. So irreversible reactions go to completion. They're like a one-way street. Think about burning a piece of wood. That's irreversible, right? You can't exactly unburn a pile of ash back into a log. But then you have reversible reactions, and these act like a continuous, dynamic back and forth under the exact same conditions. If you evaporate water in a totally closed container, that vapor condenses back into liquid at the exact same time the liquid is evaporating. The reactants are converting into products, and simultaneously, the products are converting right back into reactants. It's just a constant loop.
Now, take a look at how these curves actually converge over time. You can see the forward reaction slowing down as those initial reactants get used up, and at the exact same time, the backward reaction speeds up as more and more products are formed and become available to react in reverse. Eventually, these 2 curves completely flatten out and meet. The rates perfectly match.
And this right here is chemical equilibrium. Once we hit this exact point, observable properties, things like pressure, concentration, density, even color, they become totally constant. I mean, if you were just looking at the container from the outside, you'd probably think the reaction had completely stopped, just frozen in time. But molecularly, the tug of war is still raging. It's just perfectly matched in both directions. Moving on to Section 2, measuring the stalemate. Now that we've got the rules of the game down, let's meet the scorekeepers. How do chemists actually measure all this hidden activity? Well, this rule, the law of mass action, allows us to mathematically translate that stalemate. It basically shows that the rate of the reaction depends entirely on the active masses of the reactants at play, multiplied together, and raised to the power of their quantities in the balanced equation. It's just a remarkably precise way to calculate the push and pull of all those molecules. And this brilliantly illustrates how we actually calculate the final score of that equilibrium constant. Depending on the state of matter we're dealing with, we use either molar concentration, which we call Kc, or partial gas pressure, which we denote as Kp. Notice that Kp is strictly for the gaseous state since, pressure is the dominant factor there. And here's a fun trick. Pure solids and pure liquids are considered to have an active mass of exactly 1, so they neatly drop right out of these mathematical expressions. It makes the whole calculation surprisingly elegant. But what about the actual journey before the destination? See, the equilibrium constant K, that only tells us the final score. The reaction quotient, or Q, measures the current active score at any given moment before we hit that final K. If you track the Q line, you'll see it starts all the way down at 0 when we only have reactants, and then it climbs steadily as products form, eventually leveling out exactly at the equilibrium line. So the absolutely crucial takeaway here is that by comparing Q to K, we can predict exactly which way the reaction is going to shift to reach its balance point. If Q is less than K, the system needs more products, so it pushes forward. If Q is greater than K, well, it's overshot the mark, and it's going to shift backward to make more reactants. And when they are perfectly equal, boom, the system has successfully established equilibrium. All right, Section 3, the degree of dissociation. Because sometimes we need to know a bit more than just the direction. We need to know exactly how far apart our initial reactants were actually torn before they hit that stalemate.
We call this the degree of dissociation, symbolized by the Greek letter alpha. This fraction is basically just a measurement of breakdown. It's always going to be less than 1 unless the substance is totally, completely dissociated.
And chemists can actually cleverly calculate this by measuring the vapor density of the mixture. Why? Because as a molecule breaks apart into multiple pieces, the total volume increases, which in turn perfectly alters the density of the vapor. Pretty neat, right?
Let's shift gears to Section 4, Le Chatelier's principle. Up to now, we've looked at systems left completely to their own devices. But here's where it really gets interesting. What happens if we suddenly introduce a plot twist to our perfectly balanced system? Enter Le Chatelier's principle. Think of this as the system's absolute survival instinct. If a chemical system at equilibrium experiences a stress, like, say, a sudden change in concentration, pressure, or temperature, it's going to fight back. It will spontaneously shift its direction to neutralize the effect of that change and reestablish equilibrium under the newly changed circumstances. Let's see how this breaks down into 3 actionable rules for disrupting the system. First up, altering concentration. If you dump in more reactant, the system shifts forward to consume it. Simple enough. Second, tweaking pressure and gases. If you literally squeeze the container and increase the pressure, the system escapes that stress by shifting toward the side of the reaction with fewer moles of gas. And third, manipulating temperature. If you heat things up, the system will favor the endothermic reaction to absorb that extra heat. But if you cool it down, it'll favor the exothermic reaction to replace the lost heat. It is just this brilliantly self-correcting balancing act. And finally, Section 5, Thermodynamics of Equilibria. Let's zoom out a bit. Beyond the test tubes in closed containers, there are these massive, cosmic rules governing the spontaneity of this entire balancing act. This giant zero represents the exact value of the Gibbs free energy change, or delta G, when our system hits perfect equilibrium. Gibbs free energy is essentially what tells us if a reaction will happen spontaneously on its own without any outside help. While a negative delta G means a reaction happens spontaneously, and a positive one means it definitely won't happen without some external energy, a perfect zero means the universe has found its ultimate stable compromise. At equilibrium, the molecules have perfectly balanced their 2 deepest desires, the drive toward minimum energy and the drive toward maximum entropy, or chaos. It is literally the ultimate energetic standstill. So I'm going to leave you with this one thought to ponder. We just learned that molecules tend toward a state of maximum entropy. The universe absolutely loves chaos. But right now, countless reversible reactions are constantly adjusting inside your own body, responding to stresses and fighting back using Le Chatelier's principle just to keep you alive. So if everything naturally tends toward chaos, how is the delicate, dynamic chemical equilibrium inside you perfectly maintaining the incredible order of life itself? It is a fascinating paradox to think about. Catch you next time.